Hi, this is Group 24's demo video, and we'll start by illustrating our problem definition, which is to accurately predict NLS and LS signals to provide accurate localization for indoor systems, mainly smart home devices and sensors. So to start off, we have our notebook set up where we install all the necessary libraries to run our notebook. Next, we imported the basic libraries such as NumPy and Pandas and other plotting libraries. Next is our data preparation step, where we import the data set. After that, we show a preview of the data, the top 5 rows, to understand what rows are available and what columns and features we're working with. After that, we checked for duplicate rows and values and missing values. So in all these features, there were no missing values and no duplicate rows. So we moved on. After that, we calculated the first path amplitude and the standard deviation noise. The reason we did this is because when we were reading the DW1000 handbook and manual, we realized that the standard deviation noise and the first path amplitude had some correlation and how the quality of the receive times and worked. So in order to visualize this, we visualized whether there is a difference between the first path amplitude and the standard deviation noise. What we realized was that there was difference. There is a high number of values, which would mean that we would probably like to give more weightage to the first path amplitude rather than the standard deviation noise. Next, to check for outliers, we did a box and whiskers plot. So we saw that range, first path index, standard deviation noise, CIR power, and max noise had a lot of outliers in them. So what we did next was that we wanted to split this up. We wanted to detect the outliers and see whether there was a relationship that these outliers were because of the classification between NLS and LS. So what we did was that we did a 3D plot. So here, as you can see, for example, in first path index, you can see that for NLS and LS, there is a discrepancy where LS indicated that there were not as many outliers, but NLS signals had a lot of outliers in them. So values starting from 740 all the way to 840 were much more prominent. So because of this and other outliers stating this trend as well, we have decided to keep these outliers because we understand that this could be natural variations. Next, what we did was we started our data processing step. So first we did was, according to the DW1000 user manual again, under section 4.7, we realized that there were two formulas given. And one formula was that you could figure out the Rx power and the FP power based on the features given, and we would be able to determine whether something was N loss or L loss based on the decibels of these two differences. So we plotted out we calculated these values and we plotted out the result. So in this plot for NLS and dB in a density plot, we realized that the range of LS signals were from 0 to 10, where NLS were from mostly 0 to 30. This means that there could be some significance in identifying whether it was NLS or LS. So next, we dropped the columns for the Rx power, FP power, and the constant because we no longer needed them. And we extracted out the CIR data. And the CIR data is the 1016 columns that were samples collected in 1 nanosecond frames. So next, what we did was we separated that. We also did a correlation heat map for all other features to see whether any of the features were coinciding and determining whether N loss were helpful in determining N loss. So after that, we also did a feature importance plot where we figured that RXP ACC was the most important feature of all of them, and we also identified mainly the four least important features, which were preamp length, channel, bit rate, and PRFR. So because these values were constant, for example, channel number was always 2, they didn't affect whether you could determine N loss or L loss. Because we saw no use in these data sets, we ended up dropping them. This is just a bar graph to show how important our features were. So as you can see, preamp length all the way until PRFR had no significant use in our case. So because we didn't want to incur more computational costs, we dropped them. Next, we normalized our CIR data by RXP ACC, and then we did our train test split. So we did our train test split in 80-20 because we found that our data set was large enough to accommodate to an 80-20 split. Next, we did a statistical test. So what this statistical test was whether to see whether our features needed to be normalized or what kind of scalars we should use. So because we realized that most of these features were not normal because they didn't follow the red line and the value of it was less than 0.05, it determined that these features were not normal. Thus, we cannot use a normal scalar. We had to use other scalars such as min-max scalar. So before that, we did a PCA. So what we did first was that we identified, or we tried to see how many components we needed to retain. So we got the eigenvariance energy ratio. So we had printed out the progressive sum, and we wanted to keep 90% of our data set. So we wanted to retain 90% of the information, so we listed our component as 90%. In this graph, we also plotted it out. As you can see that the cutoff that we wanted to put was 0.9, and it reached at around 14 components. Finally, we did PCA for 14 components, and we plotted out the final the PCA data. So as you can see, this is the cumulative explained variance, which is the information retained, and these are individual n number of components and how much each component retains information in. So we retained all the way until 14. Moving on, we did the min-max scalar as because of our normalization test that the features were not normal, so we chose to use a min-max scalar instead. The next step was to use hyperparameter tuning, which we selected 6 algorithms to choose from. So of these 6 algorithms, we wanted to do hyperparameter tuning on all of them. So what we did was that we had 5 algorithms do the Bayesian optimization. So what we did was we defined each algorithm and the search parameters we want to search them between. So what Bayesian optimization does is it will find the optimal hyperparameter within this range, and it will print us out the results. So furthermore, what we did was we did an objective plot. So what this objective plot is to see the relationship between our optimization of our hyperparameters. So we did this for all of our algorithms. Finally, what we did was we used grid search CV because the multi-layer perceptron classifier was not we couldn't put the layer size into layer search because they didn't allow sets. So what I did was we used grid search instead. Though it's more exhaustive and highly computational, we opted for this just for the multi-layer classifier. So moving on, we printed out the results and found the best hyperparameters. So for example, for decision tree, the max left was 7, we should have used the square root function, and then the minimum sample split was 3. So after this, we also did scoring for the cross-validation scores, and we determined that most of the models did pass our test where it retained more than 82% score, so it meant that our data was not worth fitting. After that, we also did the train test score, where the train score was higher than all test scores, which meant that our data wasn't overfitting or underfitting, though MLP might be because the margin is quite big. So after that, we ran our chosen parameters. So for example, logistic regression, we found that 1.09 was the best coefficient to use. So we plotted that into our models and we ran the results. So we printed out confusion matrix as well as the train accuracy and test accuracy. So using this later, we'll be able to identify the best value or what is the best model to use. So we did this for all of our algorithms. Subsequently, we plotted the train and test accuracy to see which had the best test accuracy, which was random forest. Next, we also showcased the precision recall and F1 score. Again, random forest performed the best. Finally, for F1 score, random forest was the best. The reason why, and we decided to use F1 score as our main indicator because we realized that we only cared about our LS classifier. So meaning to say that because we're trying to provide accurate localization, F1 score was the most important because we wanted to determine LS rather than NLS. Thus, for using the true positive, we wanted to get the false negative and the true negative. So getting the balance between the recall and the precision was our optimal goal for the business requirements, and that's why we chose F1 score to use. Again, random forest performed the best for F1 score. Finally, we did an ROC curve. This is to see whether the line was the model had fit the optimal curve. So in this case, ROC curve, random forest did pretty well, where it almost achieved a perfect curve, as well as we did for the precision and recall score to see how well we did, and it also achieved almost a perfect curve. Thus, we can assume that random forest is our best model, and we'll be using that as our classifier. Thank you.